Maybe we can start, and yeah, I mean, others can join in the meanwhile. So, good afternoon, everyone, for and a warm welcome to all for this workshop or a webinar on machine learning for fluid mechanics. So, here we have the the best person or the right expert. We have Dr. Ricardo um, from KTH Royal Institute of Technology, Stockholm, Sweden, and he'll have we'll have a wonderful 1 hour session moving forward. And before introducing about Dr. Ricardo and about the machine learning workshop, so before that, let me introduce about the platform which is organizing this Flow Thermal Lab. So let me share my screen. Um, 1 second. Can you see my screen? Is it visible?
Yes.
Yeah. Hi. So display. Okay. So this is all about Flow Thermal Lab, and I will not take more time. Okay. So yeah. So it's about introduction to our company, the startup, and here the main goal of Flow Thermal Lab, the company, is about that we have two departments. One is all about online education, and the other part is consultancy services. So online education is all about being a helping hand to fulfill the gap between the university education and what the industry demands. So this is where we bring in with a lot of courses, online courses, webinars, workshops, from the right experts, so that students get it. They could easily get hired in industry, or they could fill this gap. That is one side of it. And the other side is about consultancy services. We are good at CFD engineering, and also about coding and other computational engineering services. So we work with a lot of companies in Europe, and also in Middle East and some other part of the world, where we provide engineering services. So this is the other part of our business. And what is more interesting, so this is where we are incubated. This is our office. We are part of the Ingenuity building at the University of Nottingham Business Park, along with many other startups. And you can see, like, when you open our website, Flow Thermal Labs, you can see various courses there. You can start with CFD foundation course, the fundamental course. Then you have different tools like ANSYS Fluent or OpenFOAM, Star CCM, or and many other courses where you need to learn the fundamentals to be expert in computational engineering. So you can also see specific courses on OpenFOAM, like OpenFOAM beginners course, programming courses on OpenFOAM, like, and then some workshops conducted specific to OpenFOAM. Then we also have a course on fluid structure interaction, again based on OpenFOAM. So there are many online courses. They are on demand courses, like you can log in anytime, and then and do it at your own pace. And there are other programming courses as well, because these are very specific to mechanical engineering or aerospace engineering, or you can say that computational engineering. Because often what happens is, you do a very general programming course, then you're it's just like a computer science student. But we have tailored the course in such a way that it is useful for mechanical engineers or aerospace engineers who are looking into computational engineering. So C++, Python, MATLAB, and all those courses are developed in that, keeping that in mind. And a lot of live workshops, as including CFD tools, including specific topics like machine learning, design of turbo machinery, multi-phase flow, and things like that. And if you want to be part of long-term batches, like live batches, like we have a mentorship program for six months long mentorship program, where we also help students to get placed in companies. So it starts from very basic fluid mechanics to tools to domain expert level, and then doing a lot of projects, and making you specific, perfect for getting hired in the industry. So these are some of the things which we are doing, and also consultancy services specific mostly into the CFD domain, and we also serve FEA, CAD, and coding domain. So this is very generic information about Flow Thermal Lab, and you can go to our website if you're interested to collaborate with us on courses, on learning courses, or developing courses, or or also on consultancy services. Please be in touch with us. So that's all from my side about Flow Thermal Lab. And now let me, thank first of all thank Dr. Ricardo for accepting my invite to be to deliver this webinar on machine learning. So let me introduce Dr. Ricardo. So Dr. Ricardo is an associate professor at the Department of Engineering Mechanics at KTH Royal Institute of Technology in Stockholm, Sweden. He studied mechanical engineering at the Polytechnic University Valencia, Spain, and PhD in mechanical and aerospace engineering from Illinois Institute of Technology, Chicago. And his research combines numerical simulation and data-driven methods to understand, control, and predict complex wall-bounded turbulence flows such as boundary layer development around wings and urban environment. And also, if you have gone through recent publications of machine learning associated with fluid mechanics, he is there in most of the publications. His name is there, be it in Nature or any top journals. You see, Dr. Ricardo is one of the main contributor to this field. So he is one of the best experts in this field in the whole world in machine learning. So it's a great honor to have Dr. Ricardo to be part of a workshop at Flow Thermal Lab, and I'm very, very thankful to Dr. Ricardo. So over to you, Professor Ricardo. So uh, I stop my video and my mic. Over to you.
Thank you very much for the very kind introduction, and thanks also for the invitation to give this seminar. I'm going to be discussing a general introduction to machine learning to fluid mechanics. So, of course, there's very advanced topics that one can look at, but here I will just discuss the basics, and I hope that it helps as an introduction for many people to get into this area. My research is funded, among others, by the ERC, the European Research Council. So let's dive into it. We start with a short introduction to machine learning. Why do we use data-driven methods? Generally because many scientific problems... So please mute yourself. Yeah, okay. Basically because many scientific problems nowadays cannot be tackled with classical approaches because of the sheer amount of data that is available. 90% of all the data ever generated was created over the last 2 years. The large volume of data available has led to the development of a new field, which is data science. And data science and data-driven discovery has been labeled as one more pillar of scientific discovery, together with theory, experiments, and simulations. And so machine learning is not replacing any method for scientific discovery, it's basically complementing these existing methods. Now, data science has to do with many fields, including mathematics, statistics, computer science, information science. In fact, the term data science was proposed by John Tukey in 1962. There's connections with machine learning, which has the more computer science aspect of optimizing algorithms, and statistical learning, which is more related to interpretable models, so models where we can actually find some meaningful conclusions. Now, if we want to classify machine learning methods, and this is just one possible classification, we start with this figure that you can see here. Artificial intelligence would be kind of like an overarching method, which is a subfield of computer science with the idea of creating machines which imitate intelligent behavior. This was a term developed by McCarthy and others in 1955 for a summer research program. So they were hoping to basically solve machine learning in one summer. That was very optimistic. It's taking a bit longer than that, but we can see different types of machine learning. The so-called artificial intelligence in a weak sense, in weak AI, we just have algorithms that are very good at very concrete and narrow tasks. And then the strong AI. And the strong AI is a bit of a sci-fi at the moment, a sci-fi concept. Strong AI has to do with algorithms that outperform humans in a very broad range of tasks. So this is going towards the goal of artificial general intelligence, which is again not something that we can see nowadays. The idea of AI is that it involves a machine that can mimic human intelligence. That's the main idea connected with AI. And some of the methods that are related to machine learning have to do with robotics, computer vision, natural language processing, voice recognition, and many others. That's AI, the general concept. A bit of a narrower concept is machine learning. So machine learning is a subfield of AI, which has to do with algorithms that have the capacity of learning without being explicitly programmed. This is a definition by Samuel in 1959. We can basically have machine learning and data-driven methods as synonyms. Again, this is something that is my personal classification. So I would just consider both machine learning and data-driven methods as the idea of building models from data using optimization. That's the definition that I would give. There's many possible ML methods: decision trees, regression, classification, clustering, and deep learning. And of course, we want to differentiate ML from AI. In machine learning, the focus is not on mimicking artificial intelligence, but on performing certain tasks by identifying patterns. That's what we want to do. So again, machine learning is narrower, artificial intelligence is broad. And even narrower than machine learning, we have the area of deep learning. So deep learning refers to a particular method within machine learning, which is using neural networks with more than one hidden layer. So you have your input layer, your output layer. In between, if you have more than one hidden layer, then you have a deep neural network. Deep neural networks work in a hierarchical way. So the first layers typically identify simpler objects in the data, like a mirror or a wheel. Then you apply a series of nonlinear operations so you can reach hierarchically a progressively more complex set of features, like a car or a motorbike. And they require large amounts of data to be trained. So that's where the concept of big data comes in, which is basically being able to store and analyze large amounts of data for extracting knowledge from it. There's essentially three types of learning in which you can actually train these ML algorithms. One is supervised learning, and in supervised learning, you have data that is labeled. So we have predictions or supervised classification. Basically, you have a ball, a bag full of balls, and some balls are blue, some balls are red, and I'm telling the algorithm, this is a blue ball, this is a red ball. Now find all the blue ones and all the red ones. The data is labeled. In unsupervised learning, I provide data, but I do not provide labels. What I provide is, well, basically ways for the algorithm to find clusters or to perform what is called unsupervised classification. In the example of the bag with balls, I would just say, look, this is a bag with balls, find patterns here. And the algorithm would, by itself, understand that some balls are blue, some balls are red, and it would classify them automatically. There's a third way to learn, and is what we call reinforcement learning. In reinforcement learning, what I provide the system with is a reward and an environment to interact with. So in reinforcement learning, the agent, the neural network or the machine learning algorithm, is interacting with the system and trying out different things in such a way that it can progressively converge to the best performing actions that maximize a reward. The reward is a measure of the quality of those actions. One example is a robot that is learning how to walk. So you would just give the robot a starting point and a final point, and you want it to, to complete this distance. And the robot would try different ways of progressing, and it would fall and crawl, and eventually it will figure out that standing up and walking is maybe the most efficient way. So in that sense, you just provide that reward as the way for the algorithm to learn, to be able to achieve the best performing solutions. Okay. AI has a big impact on many areas. Here you can see some of our work on sustainability. So we found that 79% of the sustainability targets can be achieved through AI, whereas 35% can be negatively affected. This is a very positive message, but we should also be aware of the negatives. So we can be realizing that there are negative cascading mechanisms which should be avoided, but it is certainly a very positive effect. We looked at this in Nature Communications 4 years ago. We also talked about interpretability, and it's possible to use symbolic regression to have deep neural networks that are interpretable. So we end up with an equation that reproduces the predictions of the model. This is very important if we want to use these deep learning methods for interpretability, basically. If we want to achieve sustainability goals, this needs to be done in a transparent and interpretable way. And we have also some work where we advocated the continued activities in AI research. So we would not support the stop of AI research as it was proposed last year. We have a couple of articles, one in Nature Climate Change, where we basically state that the limitations of AI systems in the future can be tackled most likely through AI research itself. So we really understand the systems better and the safeguards that could help us to better exploit them in a safe way. Finally, something that I always say to my students in all my courses is that simpler models are preferred. So this is a little joke. Changing random stuff until your program works is hacky and bad code in practice. But if you do it fast enough, it is called machine learning and it pays 4 times your current salary. What I'm trying to say with this is that you need to reach a good understanding of what you're doing, and typically simpler models are preferred rather than very complicated models where you cannot understand anything, basically. Okay. Now, let me start with the basics of deep learning and how we apply them to fluid mechanics. We're going to use this example. This is the 9-equation model of Moelis and others. In this model, what we do is basically project a lower representation of turbulence onto the Navier-Stokes equations, and we get these 9 modes. So you basically get a spatiotemporal representation of the velocity field. So we have these spatial modes, these temporal coefficients, which represent the basic ingredients in the near-world region of turbulence, and we produce a lot of data, 10,000 data sets or 4,000 time steps each. In this data set, if we go to the next slide, I'm showing you the temporal evolution of 9 coefficients and the 9 temporal coefficients of these 9 spatial modes. In this example, after 3,000 time units, the flow relaminarizes. This means that the first coefficient is constant and the rest of coefficients are 0. This is not an example that we would use for training because we don't consider relaminarization, but it's basically showing that this illustrates the presence of the near wall structures in turbulence. You can see the high and low speed streaks in the top panel, and you can see the span-wise meandering of the streaks as well, which are characteristics of the near wall region of turbulence. This is work, by the way, with Prem Srinivasan and others in physical review fluids. You can find all the codes and all the data in our repositories. This is the simplest neural network that you can find. This is the so-called multi-layer perceptron, which is very good for point predictions. This is a baseline for the performance that you can achieve with neural networks. In this MLP, multi-layer perceptron, I put my input vector on the left. This is a vector, an array with all my inputs. My output vector on the right, again, a vector with all my outputs here. In between, I have my hidden layers. And in this example, because I have 2 hidden layers, this is actually a deep neural network. In the example of temporal predictions, let's imagine that I want to predict the weather tomorrow, and the weather tomorrow has 9 variables. So the temperature, the humidity, the wind speed, and so on. I can use the 9 variables of today to predict the 9 variables of tomorrow, or I can use many previous days to predict the weather tomorrow. I can use a total of P days to predict the total of 9 variables in the next step. That means that if I use P days, the size of my input is going to be 9 times P, because I have 9 variables per day times P number of days. That can end up with a very long array with a very long list of variables in my input and a short list on the output, which is only 9 arrays. Okay, 9 variables. Good. So we have this schematic setup. If we zoom into a neuron, what I have, essentially a neural network is a bunch of matrix vector multiplications. So I have my weight matrices. These are my weights that I have on each of the layers. and my B is a bias vector. So this is just a vector that is added after doing the matrix vector multiplication. Important. If I only have this, what I have is simply a matrix vector multiplication, meaning that I can replace all my neural network by a single matrix vector operation, right? So that would not be so special. The predictive capacity from neural network comes from this nonlinear activation function that is applied after the matrix vector multiplication. This activation function, again, is a nonlinear function. In this case, I'm showing you a sigmoid, but it can be also hyperbolic tangent, a rectified linear unit. The sigmoid has this shape that I'm showing you at the bottom. This is a nonlinear function, which precisely makes the predictive capability of neural networks. This means that I cannot replace all the layers by one single operation. I need to do them separately, and I can capture nonlinearities on the data. Data is, of course, in general nonlinear, highly complex, and those nonlinear activation functions allow us to really reproduce such things. So what we are doing now is training a neural network. So when we train a neural network, what we do is use backpropagation and stochastic gradient descent to adjust these weights and biases. So these are basically the parameters of my network, which, remember, we are using to predict the evolution of those 9 coefficients in time. Okay, so if you remember what we are doing, we have this 9 equation model of Moelis. Right, we have these 9 coefficients, and we want to predict the temporal evolution using a multi-layered perceptron. Okay. Now, we typically use TensorFlow, which is a framework by Google Research with a front end of Keras. There are many other frameworks to train neural networks, but this works usually well. We need to define a loss function. The loss function in our case is going to be the mean square error between the reference and the prediction. So I want to minimize that. And I'm going to look at the evolution of the loss function as a function of the epochs. An epoch is a pass through the whole training data set in a stochastic way. So I'm going to be evaluating stochastically for the whole data set the value of the loss function. Now, the curves that you see at the bottom represent how training typically goes. So the blue line is the training curve. The training curve typically goes down with a number of epochs, which means that I adjust my data better as I see my training data more and more times. And the orange line is the validation loss. Validation loss typically is higher than the training loss because it's applied on unseen data. We usually divide the complete data set as 80% for training and 20% for validation. The training is used to basically train the parameters, so adjust the parameters of the network to fit the parameters, and the validation is unseen data that is not used for training, and I evaluate the performance of my network on that validation set, on the data that was not seen. So the validation loss is going to be typically larger than the training loss because it's on unseen data, but it typically goes down as well as the number of epochs, as the amount of training goes by. Now, we can see the example on the right where the training loss keeps going down, and the validation, after a certain point where it's going down, it starts to increase again. If the training loss gets small and the validation loss gets higher, that means that I am overfitting. I'm fitting very well the data that I have seen, but I'm not able to generalize very well to new unseen data. Typical solutions to that? Well, that means usually that you have a network that is too big for the problem that you are trying to solve. So either you increase the amount of data or you reduce the size of the network. Another possibility, if you're happy with the error level in the dip of the curve, you can stop training there and do early stopping. That's also a possibility. There is another problem or another possible issue when training neural networks, and it's the so-called underfitting. When you underfit, what you have is that your error is high. Maybe it's going down, but it's still very high. That means that you're not fitting your data even at the training stage properly. And that means that your network is too small. So you really need more parameters to be able to represent the degrees of freedom and the complexity of the data you're trying to model. Okay. Now, These are some examples of predictions of the 9 equation model, so the 9 coefficients in time, using a multi-layer perceptron. We need a very large input. We need to use 500 steps to predict the next time step. So since I have 9 variables per step, my input has a size of 4,500 to predict only 9 coefficients. This is a bit of an overkill, and you're going to see why in just a second. The flow fields look okay. They're not, the frontal view is good. The span-wise meandering of the streaks is not fantastic. We can actually see in the next figure how the mean error is, well, it's not so bad, but it's not so good. It's 10%, almost 11%. And the fluctuations exhibit 36% error. So the flow looks a bit like what it should, but there is still a lot of room for improvement. Now, if we look at the errors, we played a little bit with the architecture. We did what is called a hyperparameter tuning. So we adjusted the number of layers, the number of neurons per layer. We came up with this architecture with 5 layers and 90 neurons, where we have 3% error in the mean, which is good, but the fluctuations still exhibited more than 18% error. That's not so good. That's still a very large error. So what happens? A multi-layer perceptron is an architecture that does not really understand the temporal dependencies in time. You just have a list of inputs, and if you have more than one step, depending on where the inputs are collocated in that list, you can get an idea of temporal information, but you don't really exploit it so well. There is a different architecture, the so-called recurrent neural network, which you can see here, where I can actually exploit much more efficiently the temporal information in the data. In blue at the bottom, I have my inputs. So this would be the current step, and the previous one, and the previous one. And at the top in yellow, I'm predicting the next step. So the 9 coefficients in the next step. The key is this recurrent connection. So basically, the output of one step is connected with the input of the next step. And such a connection, which is done for all the steps, allows me to effectively exploit the temporal information in the data. If we zoom in to these elements, to these network neurons in an LSTM, you realize that I have 3 different gates. The key of these recurrent networks, and in particular of a very well-known recurrent neural network, which is the LSTM, long short-term memory network. The key of the long short-term memory network is the so-called gating mechanism. I have 3 gates. I have the forget gate, I have the input gate, and the output gate. And these gates, the only thing they do is that they add additional parameters in the network to decide the weight of the recent data and the past data. So I basically can modulate how important the old or the new information is to make my predictions. Right? That's a little bit the idea. So working with these gates, what I have is instead of a weight matrix and a bunch of weight matrices and bias vectors, I have 3 weight matrices for the forget, input, and output, and a bunch of bias vectors as well. So I have more parameters typically in an LSTM than in an MLP, and that's because of the temporal information that I'm trying to learn. Now, with LSTM, we did some parametric analysis. We actually could exploit effectively the temporal information in the data because the data is organized in time, and I can really connect one step with the next one. I'll show you the results in just a second, but you can see that right away with a quite good architecture, we get 0.45% error in the mean and only 2.5% error in the fluctuations. The instantaneous flow fields look much better, representing very well the span-wise meandering, and the mean and the fluctuations are in excellent agreement. If we look at the hyperparameter tuning, what you can see is that we can significantly outperform the MLP because the MLP is only designed for point predictions, and with LSTM we can really understand the intricacies of the temporal information in the data. In fact, more complex statistics like the wall normal fluctuations, the skewness, flatness, and the 3 components of the vorticity fluctuations are actually very well reproduced when comparing the LSTM results with the reference data. So these temporal dependencies are well captured through the LSTM gating mechanism, which is embedded in a recurrent neural network. Now, what I have is that the statistics are very well predicted, but the instantaneous coefficients, you can see that there is some deviation. The overall trend is properly captured, but we have about 13% error when predicting the first coefficient. This is because the non-equation model is a chaotic system. It's modeling turbulence, and therefore it's going to be chaotic, meaning that a very small error in the predictions is going to be accumulating over time and send us exponentially to a different trajectory, right? This is how chaotic systems work. Our prediction is very good, but any small error acts as a small variation in the initial condition, which basically through chaotic systems would take us to another trajectory. However, what we can do is try to understand if our neural network is learning the overall dynamics of the system. For example, here I'm showing you a Poincaré section of the first and third coefficients for a second coefficient equal to 0. So basically, this is a joint PDF, a joint probability density function, where I'm looking at the value of the first coefficient with respect to the third coefficient, and I'm superimposing the maps from the LSTM and the reference. You can see that both maps are completely on top of each other, meaning that the agreement is excellent. So I'm actually able to learn quite well the dynamics. There's another way to assess the dynamics, and that's through the Lyapunov exponent. So what I do with the Lyapunov exponents is that I introduce a perturbation in my initial time series, my initial trajectory, and then I integrate in time to measure the deviation with respect to the original trajectory. There is a first stage of exponential increase. This figure that you can see here is the amplitude of the perturbation in a log scale as a function of time. So that straight line in a log scale means that the increase is exponential. And then at some point, the deviation settles on a certain level, which means that we have reached another trajectory. By measuring this slope of this straight line, what I'm doing is estimate the rate of change of this exponential increase, in other words, the Lyapunov exponent. So this argument of this Lyapunov, of this exponential growth is what we call the Lyapunov exponent. You can see that the Lyapunov exponent is the same in the original system and in the prediction of the LSTM network, meaning again that we're able to very effectively reproduce the physics and the dynamics of the original system. So we don't predict exactly the same values on each instant. That's because my network has an inherent small error, but we are able to, when the correlations among coefficients and the rate of change from one trajectory to the other one, we're able to learn those. So the network is able to learn the original equations up to a very, very small level of error, which is manifested by going into another trajectory when modifying the initial conditions, essentially. So we're able to learn the dynamics of the system through the LSTM. Okay, and this is actually a quite good achievement. This is now 5 years ago, so this is quite some time since we published this paper. But at the time, it was a very good validation on the usage of different neural networks for temporal predictions in turbulence. Now, we tried more things. We worked on a minimal channel, and in a minimal channel, we did a model decomposition and predicted the temporal coefficients of POD modes. Because turbulence is multi-scale, and that's something that the non-equation model doesn't really reproduce. Since turbulence is multi-scale, then we can understand that we will have fast, medium, and slow modes. And we need one LSTM to reproduce each of those group of modes. I cannot reproduce all the range of scales automatically with an LSTM network. This is something that is alleviated when I use a transformer. Transformers are a novel architecture, or well, quite new. It's a few years ago that they are around, but still they're quite recent. And transformers are used for natural language processing initially. So the whole ChatGPT business is all based on transformers. We use it for temporal predictions in turbulence, in particular to define inflow conditions. And what we realized is through transformers, you are able to more effectively reproduce the temporal dynamics of turbulence because of the multi-scale character of the flow. Yeah, so transformers are actually quite good at this. Okay. Now, this is the basics of neural networks in terms of MLPs and recurrent neural networks. So how we can use them for predictions in turbulent flows, different turbulent flows. Now, I want to spend a bit of time on physics-informed neural networks, PINs, which are very helpful in certain fluid mechanics problems. And then I will have enough time to answer questions. So with pins, what do we do? With pins, basically what we do is take advantage of the machinery used to train neural networks to solve PDEs. In this work, led by Avasi, this is published in Physics of Fluids, we use pins to solve the steady 2D runs equations in incompressible flow. So our inputs are just the coordinates, and everything else, you can see that we have a fully connected network, an MLP. You come up with values of the variables that define my equations, my unknowns, and using automatic differentiation, I build the PDEs that govern the flow such that I can retrain my network to minimize the residual of that set of PDEs. We're using automatic differentiation, meaning that we are able to exploit the partial derivatives that we use to train a neural network to build the partial derivatives on the PDEs, which are evaluated exactly. That means that with pins, I can get away with meshes that are much coarser than what I would have in a normal run simulation, although pins is more expensive than another simulation. That's also something to keep in mind. Schematically, this is how it works. So my loss function has two terms, one supervised and one unsupervised. In this red figure, the red boundary is known information, basically boundary conditions, and the black points are collocation points where I basically evaluate the error of my PDEs. The supervised loss is the deviation with respect to the values at the boundaries. The unsupervised loss is the residual of the governing equations, the 2D runs P equations for incompressible flow. The unknowns are all of these values. So the mean velocities, U and V, the pressure, and the Reynolds stresses. So here we are solving the Reynolds stresses without a model. We are just directly solving the runs equations, taking advantage of the pins framework, the pins methodology. So, I will answer more questions at the end, but someone is asking about the difference between pins and a surrogate model. They're actually reasonably similar. I mean, a surrogate model is basically replacing the physics by a simplified model. In pins, you are solving the right equation through the machinery of the model, of building a model. So you don't really build a model per se, you build more of a function that satisfies the PDE, and then you build that function through supervised and unsupervised learning, basically. So, more things. Just to give you an idea of how easy it is to implement this in TensorFlow, these are just a bunch of lines. So you can use the tape gradient function to calculate the partial derivatives exactly. And you can find all the codes and all the data in our repository. In vinuesalab.com, you can find everything. But this is just to show you that it's quite easy to implement this in TensorFlow. Let me show you some examples of application. We started with the Falkner scan boundary layer, which is a laminar boundary layer with pressure gradient. This is a trivial problem to solve in MATLAB in just a few seconds, but this is just a proof of concept that this makes sense. So we solve these equations using MATLAB and then using the pins framework, and you can see that the results are excellent. I mean, this problem is trivial, but still we get less than 0.1% error in the deviation with respect to the reference in this case. Okay, now more examples. Let's look at a turbulent boundary layer, which is a more challenging case. In a turbulent boundary layer, we already have a stringwise development, we have turbulent fluctuations. We're going to be comparing the statistics of a DNS, of a direct numerical simulation, with the predictions of pins of those statistics. And what we can see, first of all, the mean exhibits around 1% error, a bit higher for the well-known velocity, and the Reynolds shear stress is about 6% error. To give you an idea, we compare this with run simulations. Run simulations are more expensive to run because you need to have finer meshes. With pins, you can get away with a much coarser mesh. So if you were running the same mesh, pins will be more expensive. But with pins, because of the exact derivatives, you can come up with a much coarser mesh. Then the cost is similar or even lower for pins, but the accuracy is better. we cannot get these very low errors in the rain or shear stress with runs, and with pins solving the runs equations, we can. You look at the stringwise development in terms of the shape factor and the skin friction coefficient, also the Reynolds stresses, they are in very good agreement by comparing pins and the reference data from the DNS. Here we have a pressure gradient boundary layer. This is work by Bobke and others. We have very complete databases for this case in my repositories. This is actually a moderate adverse pressure gradient case. And in this case, again, we're comparing the mean and the Reynolds shear stresses. The mean has lower errors than 1%, and the Reynolds shear stresses are still about 7%. You can see how when you have an adverse pressure gradient, the Reynolds shear stresses start to accumulate energy in the outer region, and energy which is very well reproduced and very well captured by pins. This is very important. Also, the anisotropy of the Reynolds stresses is quite well captured by this physics-informed methodology. Okay. Now, an even more complicated case would be a wing, a turbulent wing. So what I have is here is a Reynolds number of 200,000, and we can see how, with this framework, we can capture a region of a very strong average pressure gradient, of a very strong deceleration of the flow. If we look at this, and I'm showing you at the top the mean, the Reynolds shear stress, and the stringwise and wall normal fluctuations, you can see that in the mean, I'm still on the order of 1% error. In the Reynolds shear stresses between 5 and 10%. Much better than what you can get with run simulations, and the outer region is still very well captured. The mean is excellent even for cases with very, very strong adverse pressure gradients and very challenging flow conditions. So again, pins can really reproduce with high accuracy the capabilities of a run solver, even in very complex configurations. This is also applicable to the case of a periodic hill. The periodic hill is a case that is widely used in modeling. So here what I have is quite a smooth detachment and reattachment. I have a quite large region of separation, of recirculation. So this laminar, this turbulent recirculation bubble is very well reproduced by the pins approach. So here I'm showing you the prediction and the reference. The streamlines show the very good agreement between both, and the mean profiles that you can see here reflect the excellent capabilities of pins in this complex case. The mean is a slightly higher error with about 3%, and the Reynolds stresses between 15 and 30%. Once again, this is a very challenging case with separation, and we can observe that our accuracy is still pretty good. So we are able to achieve a very good level of reconstruction, even in this very complex configuration with separation, which highlights the potential of pins in this complex area. Okay. I want to also highlight that pins have been used in experimental work. We have this article in Measurement Science and Technology where we look at PIV measurements, particle image velocimetry. The mean was quite well resolved, but the fluctuations exhibited some problems, and mostly the V, the wall normal velocity, was really bad. We are comparing in the black line with highly resolved LES, so almost DNS. The PIV is the blue line, and in red I'm showing you pins. In the Reynolds stresses, pins improves a little bit the reproduction of the fluctuations, but you can see how the wall normal velocity V is in excellent agreement with the reference after using pins. So to correct experimental data, pins is a very useful tool. Also, to eliminate noise. This is another article that just got published in Measurement Science and Technology. You can see that we have the wake behind a cylinder on the top panel. In the middle panel, we added some noise, and that noise allowed us to really simulate whether pins can clean it up. And we could clean it up on the third row where the data is in excellent agreement with the first row. So you can see that the POD modes are getting good agreement. We are able to effectively clean up the data, exploiting the capability of being able to fulfill the runs equations. So basically the reference equations in such a way that we can have quite good accuracy. So to conclude the part about pins, we can use pins to correct experimental data. We can make predictions in the context of runs. I must say that for unsteady flows, it's not so easy to use pins. I mean, we did it for this case, and the results were good. But in general, it's challenging to embed temporal dependencies within pins, because we are using a multi-layer perceptron for time, as it is done for space, but there are ways of going around that. And in general, augmenting experimental data and correcting experimental data, these are areas where teams can really succeed. Okay, and I will keep it a bit shorter so there is time to answer questions. This is everything that I had for today. This was a brief introduction to machine learning for fluid mechanics. We looked at the multi-layer perceptron. We looked at recurrent networks and LSTM. We illustrated their usage in the nine-equation model of Noelis and others, so basically in a model of the near-world region of turbulence. And then I illustrated the usage of pins in a number of flows which are of progressively higher complexity involving turbulence. So we're able to actually have quite good representations of the flow in a number of cases. You can find repositories and data for everything that I talked about in this QR code. So you can just go there and download data. Everything is there. You can also find more information in my YouTube channel. So there I have a lot of lectures and a lot of summaries of my articles. So if you don't want to read the article, you can go there, look at the video, and then go back to the article to get more information. And also in social media, you can find my email and my X account. So you can really get all the information that you need there. I'm also very happy to discuss offline what you're interested in. And for now, I'll be happy to take your questions.
Thank you very much, Dr. Ricardo, for the nice presentation. Actually, few of the questions are already there on the in the chat, but there were also a lot of questions being sent by other participants who didn't join it here because of the time difference, etc. So maybe I will just ask few of the very generic question, because I've seen many of these questions are getting repeated. So one very interesting question is, like, many of the participants are very new to this field, and they would like to know what is the right way to start learning machine learning for fluid mechanics. So they are interested in the books, reference books, etc. to start with. So if you can give some recommendation, that would be.
No, for sure. I mean, I first think that you should have a deep knowledge of fluid mechanics and computational fluid dynamics first, or maybe not computational fluid dynamics if you're an experimentalist, but you need to know, you need to have deep knowledge of fluid mechanics. You cannot go the other way around. So you know about fluid mechanics, about the physics, and then you can start to learn about machine learning and data-driven methods. And there are many good resources. I like the book by Steve Branton and Nathan Kutz. That's a good reference. There's several others. I have several review papers on machine learning for computational fluid dynamics, for experiments, for different fluid mechanics applications. And then there's also a lot of resources online. I mean, Steve Branton's YouTube channel is excellent. You can also check out my channel. There's some lectures there. So I think that's a good starting point. The book of reference, again, is the one by Kutz and Branton. And then there's a lot of material online where you can expand your knowledge in more concrete areas within ML.
Perfect. Great. And there is another interesting question about, by CFD engineers. They are, those who are working in the field as CFD engineers, and they are a bit worried about machine learning and AI, whether they will lose their job in the future, or what is actually going to be the challenge, or whether machine learning is going to be complementary to the existing knowledge. So this is
that's a very good question. So I have a review paper in Nature Computational Science, which is called Enhancing a CFD with Machine Learning. So my view is that the CFD methods and algorithms have been established for decades. They're very efficient. They're the best way to discretize and integrate the Gaussian equations. With machine learning, you cannot do that as efficiently as with those methods. So my view is that machine learning will not replace CFD, but it will help and complement certain aspects of CFD. So for example, you can accelerate certain parts of the algorithm. So you can maybe have a initial condition for the Poisson solver that is very efficiently chosen to accelerate the algorithm. You can improve modeling, runs and LES, and you can develop very good reduced order models. So in that regard, I have quite some work also on that aspect, and I think there is a lot of potential for reduced order models. So long story short, they shouldn't be worried. Their CFD jobs are secure, and it doesn't hurt to learn about machine learning, to see how machine learning can help CFD and enhance many of the CFD algorithms that we're using nowadays.
Great. And another question, which is, what are the biggest misconceptions about machine learning for CFD? And another connected question is, what are the biggest challenges in application of CFD with machine learning? So
Yeah.
misconceptions and challenges.
I think the biggest misconception is what we were just discussing, that machine learning is going to replace CFD. Machine learning is not a magic wand that will solve all your problems. The most efficient way to encapsulate the fluid mechanics information is the Navier-Stokes equations. Navier-Stokes equations encapsulate the information very nicely. And if you try to represent the same amount of information with data, you will need a lot of data and a lot of resources to be able to represent the same amount of information. So machine learning is not going to be more efficient than CFD. I mean, that's at least I don't see that happening anytime. I think that's a misconception. People who want to replace CFD with machine learning, it's not about replacing, it's about complementing and accelerating. Now, what are the challenges? One of the main challenges right now is the generality. Now, you work very well for certain cases, and to be able to generalize to new cases is still a challenge. There are algorithms and methods that are going in that direction, and I think reinforcement learning in that regard is very promising, but I believe it's still a challenge to have a general enough set of machine learning models.
Great. Another question is, at what level and on what subjects should one have knowledge in order to be proficient in machine learning? So you have told us something about it in the beginning. Maybe, this is an interesting one for many people.
Yes, I mean, a starting point is a good knowledge of algebra. So it's good to revise a little bit. And if you go to my videos or Steve Branton videos, you will see a lot of lectures on linear algebra. So basically, SVD, matrix decomposition methods, optimization, that's the basis. Those are linear methods. Those are actually quite easy methods, but they still perform very well. When you start to add complexity is when you start to optimize and add nonlinearities and nonlinear activation functions and complex architectures like the recurrent neural network or the convolutional one. So architectures that are able to exploit temporal data or spatial data, then things get complicated. But if you have a good mathematical foundation from the linear algebra, it will be much easier to tackle the more complex problems later on. So, and of course, coding, to be very fluent in coding is also important. Python is nowadays the standard when looking at machine learning methods. So I think that's also a very important skill to develop.
Another question is, does advancement in machine learning bring about better methods to do turbulence modeling in CFD simulation?
Yeah, I think so. Basically, what I see most potential is in reinforcement learning because you can really dynamically adjust your model to the instantaneous state of the system. There is quite some nice work also on computer vision, on being able to identify patterns and structures in the flow that may help inform your models. And again, the challenge is the generality. But I think things are going quite quickly forward, and I see quite some progress coming this way. Yeah.
Great. One more question, which again related to challenge. What do you see as the biggest challenge in adopting machine learning for CFD applications? Do you foresee machine learning being an effective tool for the analysis of combustion CFD simulation, for example, for rocket combustion? So it's connecting it with a real world practical application.
Yeah, challenges, I mean, besides the generality that I mentioned before, I think that to be able to go to large scale applications, to flows of industrial relevance, which will require very large simulations and very large extra scale simulations, the machine learning algorithms are not designed to scale so much. They're designed to work on data sets that can be done a bit even asynchronously. You can analyze these different parts of the data set at the same time. Everything needs to be very parallel when you're running together with a large code in a large machine. So things need to be streamlined significantly. And I think there is quite some room for improvement in the libraries and the codes to be able to run on large machines. So I think that's the current challenge to run on large machines. For combustion data, yes, there is nice potential, depending on what you want to do, but you can build reduced order models quite nicely. You can build, you can also identify coherent structures of different types using machine learning in turbulent flows with combustion. So I see potential.
All right. Now, maybe we can take some questions from the chat here. About the book. Can anyone write the book name here? Maybe, if you can give the name once again, would be great.
Yes.
By Steve Brunton.
Just I will just give you the link. Brampton and Kutz. Data-driven science and engineering. I will just give you a link to the
There are
chat.
two books by him, right? So on machine learning.
Yes, I mean the one data-driven science and engineering is a good reference. They're in the second edition. They have more books, but I think this one is a good academic reference.
Then the next, for flows which are unsteady, turbulent, and multi-phase, as in Pelton turbine flows, will it be difficult to implement the machine learning?
Well, depending on what you want to do. Depending on what you want to do. If you want to analyze the flow and try to make predictions in time, if you have enough data, and there might be some challenges with the multi-phase, but making predictions in space or in time is possible. It's still being done nowadays. For modeling purposes, that's challenging. I mean, right now there is not a very good model developed with machine learning for these applications, but I think it will probably be possible in a few years.
Another question is, does machine learning have the capability to recommend optimal mesh configuration for a particular problem?
There is some work in this direction. Again, I think a very promising venue is through reinforcement learning for adaptive mesh refinement, and there is already some work that is looking at this problem.
Great. How important is it to pre-process your CFD data, meaning lower order models, before learning your machine learning model?
Well, to pre-process the data and clean up the data is essential. To build reduced order models, it depends on what you want to do. If you want to make predictions in time, it might be a good idea to build a reduced order model, so you only need to predict the temporal coefficients and not the whole flow field. If you want to control the flow, if you want to identify regions of strong fluctuation, then you don't need to build a reduced order model necessarily. You can just go directly to the full data. So it depends on what you want to do.
Exactly. Then is machine learning algorithm are superimposed with open source CFD codes yet to accelerate the analysis? I didn't get exactly what you mean, but yeah.
Well, there is work on accelerating CFD through machine learning, and there are many examples. I don't know if in commercial codes, that I cannot really tell you if that's done in commercial codes, but I mean, there are many examples in the literature of acceleration of CFD through machine learning.
Okay. How can machine learning be applied to experimental fluid mechanics?
Yeah, that's a good question. I have another review paper on that in Nature Reviews Physics. There's three categories where ML can help. One is in improving the experimental measurements, so developing better correction schemes for the sensors, basically. Another one is on being able to better design experiments, so data augmentation, digital twins, uncertainty quantification. And the third one is to better estimate and control flows in experiments. So there's a lot of potential also to be able to design new control and prediction techniques with ML.
Can it be a coupled approach of some experimental data and some high fidelity CFD data? Can it be combined in some way
Yeah,
to
absolutely.
predict better?
Absolutely, there is data augmentation where you can use numerical data to enhance your measurements, and there is also multi-fidelity frameworks where you can combine data sets from different fidelities to try to have the best possible prediction.
Great. Is it correct to use variables other than those in the formulation as input parameter in prediction algorithm?
Well, you can use as input whatever you want and as output whatever you want. I mean, you are free to do whatever you want to predict. The point is, if there are no patterns and correlations between those inputs and outputs, then the predictions will not be so good because ML algorithms look at patterns and correlations. So you should make sure that your input data is scaled properly and that is a relevant quantity to predict your outputs, basically.
There's a big question now. How can I use and apply machine learning to study the mechanism of the vortex-induced vibration around the bridge deck using data obtained from CFD simulation? Could you please provide some insight on this? And also the use of pins for prediction of amplitude and vortex-induced force. And what is the limitation of machine learning and pins in regarding this?
So first of all, I guess one way to use it in that point would be for reduced order models. So you can use reduced order models to analyze different configurations and to make predictions quite quickly. For pins, I would say that it depends on how many real measurements you have. Pins allows you to use the covariant equation, which you know, and the data that you have measured. That's one advantage of pins. If you have good, reliable data, it may be possible to use pins to make these predictions. Yes. I guess we are already reaching the end of
we are
the
all,
session.
exactly. So yeah, we are already, if you have further more questions, you can write to us. We will try to collaborate with Dr. Ricardo and get back to you. And hopefully, we will have a better course in the future with much more detailed course where you can learn machine learning with fluid mechanics in a much more structured way. And thank you, Dr. Ricardo, for your time. And it was a wonderful experience for all of us. Thank you.
Thank you very much for the invitation. It was a pleasure. And yeah, see you next time.
See you next time. Bye bye.
Bye.